right, great. Okay, yeah, I will do that. Yeah. So hi, everyone. My name is Gourab. So I wanted to start with 3 disclaimers or warnings, however you call it. The first one, I'm known for the corniness of my jokes, so I apologize in advance. Number 2, the topics that I'm going to cover are quite deep and detailed and lots of research work going on there. The purpose of this presentation is not to go in super detail and kind of teach you some of these methods, but mostly to kind of invite discussions as well as set you on a path where you can learn more about those. And then the third is trusted AI or trust in AI has been a pretty strong topic now, thanks to media as well as all sort of popular publications. It's a pretty deep and big topic. My attempt here only scratches the surface of it. So if you are disappointed that I'm not going to go into detail, I live to disappoint, so thanks. All right, with that, so this is my title slide. So you will think, OK, there is nothing there. But there is. It's just in black. So the topic of the presentation is black box no more. See, I gave you disclaimer that it will be corny. So the choice of the title was either that or how to train AI. So I chose with the less cornier one, hopefully. But one of the things that we hear quite a lot about is the idea of interpretable models or interpretable analytics. And Cynthia Rudin recently have been pretty vocal about, like, there is a class of models that are interpretable, and then there is the other class that are bad or not interpretable. She didn't say bad, so don't misquote her for that. And there is, in the industries that we work with, there is a quite popular notion that linear models are interpretable. Who here believes linear models are interpretable? OK, I see a few hands. I think a lot of people want to raise their hands internally, but they're like, I don't know, is this a trap, and so on. So those who are building linear models, how many are familiar with Bartlett's test? OK, I don't see any hand. OK, one hand. That's great. How many are familiar with Levene's test? OK, one hand, 2 hands. Great. There are around 10 other tests on the same exact topic, which is heteroskedasticity or homoskedasticity of linear models. So we are believing of linear models interpretability, but without those tests being significant, we cannot really run linear models, first of all. So not so interpretable in that sense. How many people here know the origin of why 0.05 is the statistical significance cutoff for p-value? OK, it was because Fisher just liked 0.05. He wrote it that I think it's a good number. So that's how we strongly feel about linear models and the coefficients and the p-values of that. But, well, it's not as hunky-dory of a story. In fact, many would argue that linear models are not so interpretable, mainly because they also don't work most of the scenarios. And some of the reasons for that is our reality is not as linear. Our reality, the data structures, et cetera, are not necessarily linear. So while it is very transparent because you can see the formula, it tends to be something like this, a transparent but useless thing in most of the scenario. That's the only reason to put this for. There is no relation with linear model. I just Google search for a transparent but useless object. But in that context, machine learning model in my mind is less a black box, more like a tesseract. If you are a Marvel fan, you probably are familiar with this, which is a really powerful model or powerful analytics tool, but somehow kind of you don't really know what's going on inside. And the worry about machine learning model is more a war between fear. So if early Captain America, if you have seen, you will see Red Skull really trying to touch the Tesseract, which is a really strong one, and his hand is burning, and it's kind of like scared and looking really beautiful there, versus more recent Thanos, who is carrying it with confidence. So it's more about fear versus confidence than anything else. So what would actually dispel that fear? And the rest of the presentation, I'm going to try to talk about a few tools that hopefully dispels that fear. Hopefully we can learn a little bit more about and be less dogmatic about a particular type of model being interpretable, and be more agnostic and try to see what sort of questions are we trying to answer so that we feel comfortable. So first dogma is forget about the formula and think about three main questions to make it really simple. One, what are the factors that are driving my model overall? Two, how are the factors driving my model overall? And three, how are the factors driving any one single prediction? So I'm just going to try to cover these three questions, and hopefully that gets me some little bit more confidence. So the first one, what are the factors that are driving my model overall? It's also known as the concept of feature importance. What I'm trying to get out of this is a somewhat ranking of different predictive features that I'm putting in my model. In the linear regression world, if you are familiar with coefficients, this is probably closest to the absolute value of a coefficient. So some sort of a magnitude of effect for any one particular feature. Now, there are many different methods, but mainly the ones that are most popular are either what we call permutation-based approach, or leave one out approach, or leave a variable out approach, or a pretty much algorithm-specific or tree-based algorithm-specific importance methods. The first two, I put it first two because they are model agnostic. So you don't really need a specific type of model to be using those tools. The first one basically tries to see whether if you keep everything else fixed and if you change the order of values of a particular column, how does the model react to that? How dependent the model's performance is on that particular shuffling operation. The second one, you leave that column out and see and compare with when you include a variable versus not. And then the third one kind of looks at when you are building a tree, each decisions you're making in terms of building that decision tree, how does that matter for different variables? So these are just three different techniques to use. And there are many more. And many of them has pros and cons. So I'm not going to go and start a debate on that. But in terms of usage, if you see in industry, these usually are used either to select features. So a fintech organization used to buy a lot of third-party data from elsewhere. It costs a lot of money to buy third-party. No offense to the data vendors in here. But basically, they don't know which one has the value, which one doesn't, right? So you can look at the feature importance. You can look at the ranking of the different variables, no matter which model you build. And you can try to see which ones are actually driving your model and which ones are not. And if the third-party data sources are not really driving your model, you might not want to buy them. It could also be because you want to find some sort of insights. So AML, or anti-money laundering problem, you're trying to predict which transactions have some bad transactions in it. And sometimes that can be related to much more wider crime, like terrorist attacks and so on. So the type of behaviors will be your predictors, and you will be able to see or have a more story around which type of factors are actually driving bad behaviors in transactions. Also, a result by using feature impact. No other, no special model, any model, you can actually use that. Or it could be purely because you want to improve your analytics or results accuracy more. Because when you want to do something like this, your model always depends on whether the features were clean, whether they're good data. I always hear this garbage in, garbage out sort of concept. I think people just like saying it. It like has a lot of garbage in it. But main thing is you don't really need to clean all your data, but you need to know which ones are a driving factor for you and whether you want to focus on that or not. So model improvement can also be a reason. One of the biggest reasons for feature impact or feature selection particularly is making predictions. So when you actually build model, adding more predictors make the models better. When you are starting to make predictions, adding more variables actually make the predictions slower. and more complicated. So what actually is a gain in terms of modeling actually is a cost in terms of making predictions, where your business value actually lies. So a lot of people actually will be using feature impact or importance to guide that. Okay? The next question that we were going to ask is, how are the factors driving my model overall? So I know that these are the factors that are important, but how exactly? What is the directionality of it? So in the coefficient world, that will be the sign of the coefficients. Is it positive? Is it negative? Is it increasing with the target? Is it decreasing with the target? And so on. We call in DataRobot language, but in general, let's call it feature effect. So what is the effect direction of features? And there are many different ways of doing it. One of the early ones is called ice curve, where basically what you're trying to do is you're fixing everything else. And for any particular variable C, what if that particular value of the variable changes, and how does the model prediction ranges change with that? So kind of creating this world where everything is frozen, and this one feature is what you're changing and seeing the model's trajectory with that. So ice curves are really difficult to look at, because look, like all these lines are moving. It's like, you know, New York subway. But instead, you can summarize that with a thing called partial dependence plot, which is basically average of ice curves. And you can see for a particular variable what is the average direction of change when everything else stays same, and how does the model interpret that. If that looks a little bit like a line being drawn through many points, that is actually intentional. So for a linear regression, the coefficients, and when you plot those coefficients to draw a line, actually has a pretty good connection with the partial dependence plot. So it is actually extension of the idea of coefficients in machine learning, but a really important tool to have. And then you can expand it more. So why stop at one variable? Let's do two variables at a time. So if you look at scikit-learn two-way partial dependence plot, there is a very famous examples. So I'm not going to go into too much detail, but the way to think about it is, why just one variable? How are the two variables jointly influencing the model, and what is the direction of going on? Sometimes clients that we work with get super excited and want to visualize three-way partial dependence and four-way partial dependence. Unfortunately, we cannot plot things over time like that yet, right? So we cannot necessarily visualize, but there is a lot of value in understanding these different type of interactions and so on, and these tools help you with that. One of the example that I will give is price versus sales. So you're trying to predict sales, and you know that the price is a pretty important point because with increasing price, unless you are in Silicon Valley, you're probably selling less for a product. Here, you go to Whole Foods instead of Trader Joe's. So, but if you actually look at the pure descriptive plot of what happens with increasing price and sales, here the y-axis here is on this side is the volume of sales, or whether the sales will happen or not. X-axis is the price of a particular product. And if you see, like, this line is kind of shows the scatter plot almost, or kind of a group by average over these different values, which is showing kind of like a flat line. So you don't really know whether it's going on or not. But a model can actually help kind of declutter the different effects that are going in. And if you look at a partial dependence plot of the same, using any model, once again, model agnostic, no specific model here, you can actually see this sort of an effect, where you will see this is actually Tropicana orange juice, and this is around $6. This is around, this is actually around $3.5. This is around, the next jump is around 4, and then the next jump is around 6. So you can kind of see that there are a few price points where the sale actually takes a dip once you increase that particular price point. So these sort of things are not coming necessarily out of linear model, and you can actually explain using whatever model underneath by using these tools. The final question was, how are the factors driving any one prediction? So it's good that we looked at overall effect. What are the variables overall are affecting something, or individually for a particular variable, what the direction is. But what if I made predictions for you or you? Is that going to be the same variables influencing both of us? Probably not. If it were so, all of our FICO credit score will have the same reasons why it's so low. I'm not saying it's low for us. But reason codes, our prediction explanations, are there to provide individual explanations for each predictions, which is the next realm of questioning. So I don't just want to get a prediction. I actually also want to know why that prediction is high or low, or what is driving that particular prediction. So two records can have the exact same predictions, but can have very different type of explanations. And there are many tools. So the classic tool here for a really long period of time, by the way, linear regression doesn't really have anything very specific to that from a regression framework, because it always talks about coefficients as on kind of an average across the population, right? But here, the classic one is called LIME. So LIME, essentially what it tries to do is, for a particular prediction, it tries to look at what's around it, tries to fit a line with it, and then see what's the slope of the line, what factors are driving that line, and so on. So it kind of tries to look at locally, for a particular predictions, what are the model agnostic ways of seeing which direction it's going. There is a more recent one that is getting really, really popular, is in the Shapley value related prediction explanations. Shapley value is a game theoretic concept, really, really interesting. I find it a little bit complicated to explain sometimes, but it's really valuable. Basically, the idea is, think of all the different features as players in a game, and they are you're kind of like dividing the like the joint kitty in among who is attributing what to that game. So you're kind of like trying to see who is actually driving at an individual level for that game. Now, the LIME used to be really, really popular for a really long period of time. You will also hear K-LIME or other versions of LIME. Lately, it has become more of a lemon than lime because of lots of statistical issues that come out with it. And also computationally, it's really difficult. And more SHAP is becoming the cool one. So that's SHAP, get it? Yeah. So it's becoming more and more cool. But there is a mystery entrant in here, which we cannot talk too much about. By the way, when you search for mysterious in Google, only men's photo comes, and like the first half is all men. So I had to specifically get away from my gender bias and found a mysterious woman's photo. But the prediction explanation, there are new methods there. This one, and I'm not going to go into too much detail here because it's yet to be published, but kind of similar to the idea of earlier what we were saying about ice curve. So if you keep everything else fixed, and if you just change that one particular variable, how does the effect changes for that particular prediction? That's kind of the underlying idea. But all of these are basically making explanations available for individual prediction. So far, and I'm going to go back a bit, just the three questions that we tried to ask, and this is going to be the kind of the crux of the thing, is what are the factors that are driving my model overall, no matter what your model algorithm is? How are the factors driving my model overall? And for each predictions, what are the factors driving that particular prediction? And the main takeaway that I want everyone to take away from here, that was a repetition of the same word, is these are model agnostic tools. And you have to trust model agnostic tools more than model specific. Because the same model will not work in every scenario. Same linear model will not work. Even tree-based model will not work, or some other models will not work. So you have to trust from an interpretability-wise as much model agnostic that we can go. But if we do answer all of these questions, hopefully the fear gets assuaged a little bit. If you go into industries like regulated industry, there is still a lot of myth, and you guys will be going into that industry and wielding all of these tools. But without kind of getting the interpretability behind it, it will be really difficult to explain that. So with that, hopefully, this happens, where Thanos breaks the shell of the model and get the space stone. And this is exactly what will happen when you build a model that you can understand. This is how a data scientist looks when they get an interpretable model. And they wield the power of that. So hopefully that helps with that model explanation and so on. So that's it for the thing. So any questions I can answer.
All right. Great. Thanks, Gourab. Questions? We got one right here on this side. We've got a couple of mics. We'll take a question right here. Thank you. Yeah, just wait for the mic. Yeah, thanks.
First, I just want to thank you so much for that presentation. So actually, our group's capstone, which we just finished, is actually on model interpretability.
Nice.
So I'm very excited to hear you present it, and you were much more humorous than our group was when we did it. So the one thing that our group found when we were doing our project is there's a lot of new so Lime and actually SHAP was the main thing that we presented for our capstone as well. But one thing that we found was there's a lot of new state-of-the-art techniques, some of which are specific to only a few, it's like deep learning or neural nets. Yeah. I know you mentioned there was like one model that hasn't been published, but is that kind of what your company is working on, and kind of what is the main contribution if it's not, if it can be disclosed?
Yeah, good question. So yeah, so prediction explanation or explanation around predictions right now is probably the most active area of interest for a machine learning researcher. Used to be deep learning architecture before, but now I think that's where we are going more, which is great. Sorry, was there? Oh, I have been 3 years at DataRobot, that's why. I'm really proud. Yeah. So sorry. One thing is it's going to be very difficult to keep up with all of the methods. There will be things emerging and things going out of fashion. The main thing is how you can explain it. Because SHAP, for example, is extremely good in capturing a lot of the situations under turbulation. If you have noisy data, you have induced random noises and things like that, SHAP can do really well. There are some other cool way of talking about SHAP. But when it comes to like really convincing the business folks, you might have to have an arsenal of tools so that you can explain it different ways. Same with the permutation importance or other things. So just today, I was thinking, we were having a conversation in our internal Slack channel, is permutation importance has its own bad things. Although it's a kind of industry standard or going towards industry standard now, because it doesn't really answer whether a model need a variable or not, but it's more about whether you take out or whether you introduce something in that model, whether the model will be resilient to that or not. So it's a kind of like different type of questions that you can ask. My general suggestion will be pick a few, go really deep, and really try to understand what's actually happening internally. And don't trust a particular method just because it's being published and everyone is talking about, because the rigorous of experimentation research here is not as rigorous as we think it is. If you change the data structure, these methods really behave very differently. For our organization, we are working on something, and we actually are doing some empirical study to compare so that we can do some more better recommendation than just one method.
Thank you.
Okay. Other questions? We've got one right in the center there. Second row from the back. Yep, right there.
Hi. First, I wanted to say I like the Avengers reference. So I actually use DataRobot at work, and we showed it as vision because it helps us get insights into our models. Cool. A question I had, I really like how you can basically just drag a data set in there, drop it, and it runs automatically. So a lot of the stuff I was doing previously, I was kind of able to automate that. I'm curious if you guys are thinking ahead towards automating other insights. So could you do, say, clustering techniques or topic modeling on like natural language processing, things like that, that basically you can just drag data in and get more insights that aren't there currently? Yeah.
Good question. He's not planted, by the way. I did not plant. I don't think we met even before, but okay. But I will get you a coffee afterwards. No, so I think that's a great question. So automated machine learning right now, I'm going to try to generalize it a little bit more instead of DataRobot. Automated machine learning is a pretty big hot topic right now. A lot of people are trying to automate machine learning workflow so that it can be scaled faster and made more productive and so on. And there are different things in that entire life cycle that can be automated. And some cannot be automated or yet hasn't been automated. I think from our perspective, we focus on predictive modeling primarily and not the unsupervised type of more insights, because predictive modeling usually drives decisions, whereas insights are more about kind of retrospective, and then maybe it will drive it. It's a little bit indirect route. towards it. And another reason why is the clustering type of problems. If you peel a few layers, it looks like actually, it turns out to be, if you frame it the right way, it can be a supervised problem. So, there are different type of use cases that can have that in different level. So that's one of the reasons. But having said that, that is something I think automated machine learning will have to kind of cover going forward, because there's two different directions it's going to grow in automation. One is which type of tasks you're doing in a modeling lifecycle. Let's say you have the model. Are you starting from automating data management, data prep, modeling, validation, deployment, model management, consumption, and how wide you can go in that automation cycle, as well as how deep you can go. And for the modeling perspective, the depth will come from different type of use cases, how many different type of use cases we can do. So maybe supervised is one, but then time series is another, and then unsupervised another, and so on. It's a little bit difficult to automate unsupervised, though, just to close that loop, because unsupervised, there is no way of validating. I mean, for clustering, without a particular way of saying, OK, this cluster makes sense, there is no clear-cut way of saying this is right. It's kind of like, let's do scree plot, let's look at the, kind of like whether the clusters are differentiated enough. But that's not like really saying that it's a meaningful cluster. It's kind of like a data-driven way. And that same thing goes for other things like topic modeling as well. You need some interpretability on your side to actually complement that. Yeah, that makes sense. So that's why I think it's a little bit late entrant, in my opinion, in the AutoML.
Thank you.
OK, got one towards the front here. Thank you.
I can repeat the question if that's.
Got it. Go ahead.
Yeah, thanks for the presentation. My question is, how strong is the independence assumption in these?
Good question. Very, very good question. So what I think you're referring to is, for linear regression models, the classic OLS, or ordinary least square regression model, assumes that the rows that are coming in your data set are independent from each other. The question is whether machine learning models do require that same sort of assumptions or not, and how these are kind of being affected by it. So machine learning models look at it slightly differently when it looks at independence model, independence kind of assumption. It basically creates a validation system that will be more reflective of how you want to actually kind of robustify your analysis. So just an example problem is time series are definitely that you don't have any independence between the different rows, because your previous time is you're dependent on your previous observation. So rows right next to each other are observant of that, right? So in like if you don't want to do any sort of trend or projection problems, typical time series problems in regression is treated by adding some random effect or modeling the covariance between the rows in some ways and so on. Whereas machine learning basically says, let me create a validation framework where I will build in some things that my model will make it robust against that correlation. So if you don't have any time component, you will want to do something like a grouped validation or grouped partitioning, where you want to kind of preserve or create, and I can go into detail, I'm not going to it right now, but how you preserve the correlation and make the model robust to that by predicting it on a completely different cluster or a completely different related row. With time series, for example, you do that by partitioning based on time. And so because you cannot go back in history and predict for future without kind of having a temporal order in partitioning. So most of these techniques kind of follow that same validation or partitioning structure instead of an assumption. So assumption basically says you have to be independent, otherwise you're not valid. Here it says, OK, you're not independent. Let me create some situations that mimics the risks that you think will come out of non-independence.
All right.
Yes?
Actually, I was referring to the independence of the columns.
Oh, yeah, multicollinearity. Yes.
Because you mentioned that you have to freeze a variable.
Right.
You only freeze if they're all independent.
Right. In fact, feature impact will actually show you multicollinearity better. Because when you keep everything else fixed and you shuffle one thing, and if they are related, their marginal effect will be lower. So it will actually show up less. So what happens in machine learning models oftentimes that if there are lots of multicollinear variable, the model kind of divides the effect among all of those. That's one kind of things that happen. And some extremely bad scenarios, what will happen is it will make a positive weight on something and negative weight on something to kind of go in the middle. One of the things the problem refers to is, though, what are you looking to achieve? If you are looking to achieve a model where you know exactly the variable effect for each of those because you have to tell a specific story for this variable, versus you're looking for overall accuracy and understanding of the model and what drives the factor or not. Linear regression, for example, if you have multicollinearity, your R-square or accuracy measures don't really go down. What really it affects is individual variables, p-values, and standard errors, and things like that. Similar to here, if you're not worried about being really correct about what is the underlying kind of generation model for the different features, you don't care if they are divided effect among other things because your accuracy is not going to go down. But feature impact and partial dependence both are more robust towards multicollinearity, because if you see multicollinearity, partial dependence will go flat or feature importance will go kind of lower in the down. There are still other ways it affects still. So you still need a human understanding to kind of go deeper and see, okay, these models are, these things are make sense. We have, within DataRobot, we actually have a built-in kind of heuristics that we check when we see, okay, if you have multiple variables in the feature impact, if they're redundant, if one of them should be replaced and you should be still fine. And we do kind of do those things as well. There is no replacement for looking at the variables and trying to understand what they're doing with each other. No model will get you there without you thinking about it.
All right. Gourab, thank you so much.
All right, thanks, guys.